Hey, welcome to N is for Networking. I'm Ethan Banks with Holly Metlitsky, and the format here is I've been doing networking since the 90s, and Holly's been at it for only a few years, and I have scars, well, she's getting them. And so we talk and compare notes and ask questions, and hopefully we're going to help you understand hard networking concepts in a simple way. So you're a university student maybe, and you're learning networking, or you're in marketing, or you're a new SE working for a networking technology vendor, or maybe you're working on your JNCIA or your CCNA. This show should help you out. So send your comments, your questions, and your well actuallys to packetpushers.net/follow-up, and that'll help us with errors we make or badly phrased explanations that might lead people astray. And we hope that we don't make any mistakes. But if we do want to hear about them, and we can take it. We promise we can take your criticism. It's okay. Today's episode, we're going to discuss the routing protocol Open Shortest Path First, OSPF, regarding neighbor formation and a few basic timers that are related to that. We got a lot to discuss, so let's get into it. I apologize for my voice. I'm coming off of a cold, and so if I sound congested, I am. It's been a rough week with the cold, I'll tell you. So, Holly, let's get the first question over to you. I know this has come up in your studies recently here, and that is, before we get into the whole neighbor formation thing, I got a weird question to throw at you. OSPF, is it TCP or UDP?
For a little bit of background for anyone who's listening, I've been going through the JNCIP Enterprise training. So this week happened to coincide with my OSPF course, and I have not thought about this question until I came across it in the training. So I'm really glad that I did that, because if you had asked me this 2 weeks ago, I would have been like, TCP, UDP, I don't know. No one's mentioned anything about either in OSPF. And that's because OSPF doesn't actually use TCP or UDP.
Right. What does it do? What does it use?
Now that's the question, which I also came across this week and caused some confusion for me. It uses protocol number 89, or it uses its own method of, I guess, encapsulating its data and sending it. Mm-hmm. And I guess before we started recording this, I already had questions. So my question, which I'm sure anybody who's looked at OSPF might have, and has bumped into this type 89, might have had a similar question, but what does that mean?
So what that means is IP as a protocol has a bunch of different protocol numbers that have been assigned to it. So we think of TCP and UDP all the time because we use those, and so many other protocols are riding on top of TCP or UDP as their transport number, and so, or as their transport type. And we don't think about anything other than TCP or UDP. It's like it's those two. But there's another type that I'll throw out there, ICMP, which is pings and so on, fall under ICMP. That's not TCP or UDP. It's ICMP. It's its own thing. It's a different sort of IP protocol. There is a long list of IP protocol numbers, and if you do a search for IANA, the Internet Assigned Numbers Authority, IANA, and search for IANA protocol numbers, you'll come up with a document that's a whole list of protocol numbers. So, for example, ICMP I just mentioned, that shows up as IP protocol number 1. TCP, which we're so familiar with, shows up as IP protocol number 6. UDP shows up as IP protocol number 17. OSPF, that we were just talking about, shows up as IP protocol number 89. That is, there are a whole bunch of IP protocols that have been assigned numbers and TCP and UDP are just part of a very long list of IP protocols that have been defined. And so where does that number show up? Yeah. Like, does it show up on the wire, I guess, is another question. And again, just before we hit recording, I was like, boy, I'm not sure about that. I had to think about that for a second, and I did a super quick Wireshark capture. And yeah, it's in the IP header. If you look at the IP header, there is an IP protocol field, an 8-bit field that will define that and tell you. And the point of it then is to tell your TCP/IP protocol stack on your computer, hey, this is the kind of data that's coming next. So if you're looking inside your IP payload, it's this kind of data that's coming. It's TCP, it's UDP, it's OSPF, it's whatever it is, based on the number that is encoded in the protocol field of the IP header. Does that help?
Yes, it does help. And initially, when I saw this number, for some reason, as trainings do, it didn't really specify that bit of it, that's actually in the header. In some ways, you could say that maybe the packet is like encapsulated with the header, saying, okay, well, this is what's inside. Like you said, this is what's being used to transport that packet. So if it was TCP, that would be, I'm assuming you would have seen the protocol number for that instead of 89 for OSPF.
Exactly. And that's not an uncommon thing in headers, to inform the decoder of what's coming next. Hey, what's inside of me is this upcoming thing. So, for example, in Ethernet, I don't think this is a field we talked about, but there's an ether type field. Ether type can tell you details about what's in the Ethernet frame and how to decode the Ethernet frame in a particular way, for example. So it gives you a clue as to what's coming next. So it's a thing you'll run into periodically if you get into packet decodes and so on. Kind of an important field. So I asked you a misleading question. I said, is OSPF TCP or UDP? That was a lie. That's a false question. OSPF
You've done this before with UDP and TCP, so I was prepared.
So it's its own thing. And in your study notes, you had identified 5 different packet types that we don't need to go through all of them, I guess, but I thought it was just noteworthy that, these packet types, again, they're not TCP or UDP. These are OSPF packet types that your code would know to decode what's coming next, because in the IP header, it's like, oh, this is protocol 89, so I should decode what's coming next, and these 5 packet types in accordance with that. That should be my decoding algorithm. So you, in your notes here, you mentioned like type 1 packet is a hello packet, and a type 2 is a database description packet, and so on. So that's just the unique language of OSPF coming under the category of IP.
And I think just one thing to add here on these packet types was, if you know OSPF, you usually think about, which I guess we'll get to in a later episode, but you get to like LSAs, link state advertisements. And I guess my brain, as usual, was like 10 steps ahead, and I got to these packet types. And like, I know that there are these packet types, but we've got LSAs too. And I think what's important is these are just packet types. This is before you've even gotten to LSAs. And I think initially my brain wanted to be like, oh yeah, these are LSAs as well. And I was like, no, honey, we haven't gone to LSAs. This is pre-LSA. These are just OSPF packet types.
The packet types are something that will carry an LSA. Like in the case of looking at your list of packet types here that are in our notes, a type 4, a link state update packet type would carry an LSA, a link state advertisement. That's what's going to be in there, if I'm looking at that correctly. A type 5 would carry a link state acknowledgement, and so on. A type 1 packet is going to carry a hello. So these different types of packets are going to carry specific OSPF messages. It's the container, it's the format of the packet to carry that specific OSPF payload, that sort of information. Again, does that help?
Yeah, it does.
Yeah, okay. Because we got to frame it some way. We got to.
Yes.
If we were to use my friend Russ White would describe this as marshalling. How do we describe the information? How do we format the information on the wire to get it from point A to point B? We got to marshal it somehow. So these packet types are like this. This is how we're going to format this data. Yeah. And we're not going to talk about link state advertisements they're going to come up in our conversation today, but I think there's a whole episode to devote to different link state advertisements and Boy, because that's a whole lot of information, and
Tell
we're
me about
already
it.
however many minutes in, and we haven't even gotten to neighbor formation. So I guess that's my next question then. Let's move on from OSPF and its protocol type and things about packets to, well, how do we form an OSPF network? How do
Hmm.
we actually create routing protocol conversations between routers speaking OSPF? There is some relationships that have to form here. Did you go through that process? And you're fresh studying this, so I'm just going to keep seeing what you remember.
Well, yes and no. I think what I realized is the specific training I'm doing has skipped. It's assuming you know the basics. So I've gone into
Hmm.
more of step three. But yes,
You
it
said
definitely covers
you're working at the JNCIP
P.
professional
Yes.
level. Okay,
Yeah.
okay. So it's
Um,
expecting you picked up something from your JNCIA level
one would hope.
training on this. Okay,
Yeah, because I've done the associate and the specialist come before this.
okay.
So it's not getting to the nitty gritty. But it definitely covers this neighbor formation because obviously that's fundamental to OSPF.
Okay. So, to form an OSPF network,
Hmm.
we have to have the OSPF routers form neighbor relationships with each other. That's the fundamental building block here. OSPF neighbors that are sharing the same segment and that are speaking OSPF into that segment will discover each other and become neighbors. And then once they are as a part of that neighbor relationship, they may, depending on how deep of a neighbor relationship they form, they will or they won't exchange database information, and we're gonna cover some of those
Hmm.
details here, because you can be a neighbor and not exchange database information. You can actually know about each other on the wire, or you can be a fully adjacent neighbor and exchange all of your databases with each other on the wire. So there's some subtlety there
And have the
that we need
same
to go through.
database, which
Yes, and of
is
course they will have
key.
the same database. Yes, yes. And another thing worth mentioning here is we're going to talk about this as for OSPF version 2.
Mhm.
There is also OSPF version 3, which incorporates IPv6, but we're going to focus on just version 2 today, which is IPv4. V3 does V4 and V6, as I recall, but we'll
Yes.
just stick with V2 today. Okay, so if we want to talk about OSPF routers becoming neighbors, how do they discover each other, Holly?
So that's that first type packet we spoke about. You're going to have to try and see who else is there. Am I the only route on this network? So you would likely send out a hello packet, like anybody else there? And maybe if there is, you'll get a hello in response.
Mm-hmm.
And now you know, well, there's me and there's you and maybe some others.
Yes, yes. So exactly right. There's hello packets, an OSPF router that you have configured on the router to speak hello out of, or to speak OSPF out a particular interface. You are going to be sending hellos. Now, where are hellos sent to? That is, what address am I sending my hellos to?
So that's a multicast address. It's 224.0.0.5.
Mm-hmm.
So it's going because it doesn't know what's out there on the network. So it's not going to send it to a specific router because it's checking, well, are there any other OSPF routers there? So that's that multicast address that it's going to send out.
Now, what do you know about multicast? What does that mean to you?
Um, I'm not sure where we're going with this, but to me, I mean, multicast is you sending it out. I don't want to use the wrong term here, but you sending it out.
Let's back up a second.
Yeah.
Maybe if I send something to a broadcast address, if I broadcast something, what does that mean? Who's going to hear that broadcast?
That's going to be everybody within that broadcast domain.
Everybody in that broadcast domain. Okay. So multicast is similar, but different. Can you explain how broadcast and multicast are different?
Sure. So, I mean, I would say multicast isn't necessarily... No, I'm about to butcher this, Ethan. I'm not prepared for this question.
Okay, it's good, it's good. So, okay, that's fine. So a multicast is a broadcast, but only for people that are that are participating in that particular multicast group. And so when I send a multicast out to 224.0.0.5, that is a specific kind of reserved multicast group that is reserved for all OSPF routers. So if I am an OSPF router, I am, as a part of being an OSPF router, going to be listening to any multicast that are sent to 224.0.0.5. If I'm not an OSPF router and a packet goes by for 224.0.0.5, I'm ignoring that. I don't care about that. I'm not listening to that. I'm not gonna take that packet in and act upon it or do anything with it. As opposed to a broadcast where, everybody hears a broadcast. So a multicast is like a selective broadcast. Okay. I'm choosing to participate in the multicast group, in this case 224.0.0.5, because I'm an OSPF router. And therefore, when I see a multicast message go to that 224.0.0.5 multicast IP address, I'm going to therefore act on that. So when I send a multicast hello out to the multicast group 224.0.0.5, if I'm an OSPF router, I am participating in 224.0.0.5, I'm going to see that hello message go by and act on it and do something with it. Multicast isn't unique to OSPF is really my point here.
Yeah.
Multicast is a networking technology where selected applications, selected IP, or selected programs, if you will, can listen and or send traffic to those IP addresses. They can receive traffic on that multicast IP address. They can send traffic on that multicast IP address. And routers can build complex multicast trees and so on. A whole other conversation for a whole other day. I mostly just wanted to highlight that if you're like, oh, this 224.0.0.5 multicast thing, it's an OSPF thing. Nah, it's its own thing that multicast or that OSPF is using to communicate to other OSPF routers in a selected way.
Is that IP address OSPF multicast specific? So 224.0.0.5, is that specific to OSPF?
Yes, it is a multicast address that is reserved for OSPF communication specifically. Exactly. And there's a list of them. There's not tons of them, but that's another one of those lists. Like we were talking about IANA protocol numbers earlier in the show. There's a list of reserved multicast addresses that are out there as well. And then there are multicast addresses that you can just use, like your service provider sharing IPTV via multicast. You may have your own scheme of multicast addresses that you're using. It's a whole other thing you can dig into. Yeah. All right. So that was a big.
The good news is, as you explained it, I wouldn't have butchered it. I just would have left out some facts. So I'm like,
okay,
I'm fine. I do know some things.
I love the lack of confidence. Oh, that's fun. Okay. So all of that to explain, we're sending a hello message out to 224.0.0.5. That is a multicast address reserved for OSPF routers. Anyone else in OSPF that is an OSPF router is going to hear that hello and should respond to it. So this is the beginning of forming a neighbor relationship, is this exchange of hellos. A hello comes out from a router receives the hello gets sent back. Oh yeah, hey, you're an OSPF router. I saw you, and this is me. And so, if you look in the hello messages, there's going to be an encoding of the router ID of the originating OSPF router, and then the response will go back saying with that original router ID, and then its own router ID as well. That will be sent on the wire as well.
So now we've got multiple routers in this network.
Yep. Well, let's keep it to two. Let's keep it to two for now. Yeah, we got two.
Then it doesn't help my question. It doesn't help my question.
Oh, okay. Then go ahead.
So we've got
wherever you're going.
Okay, let's go with two, right? They're both on the network. They come up at the same time. Who's going to send that first hello packet first? Like, who gets to, who goes, I guess, who goes first? Or do they both multicast it out and everybody's going to respond to everybody, kind of a thing?
They'll both for that process. They'll both like there's no. Is there some kind of a back off timer or something? As far as I know, as soon as they are up on the wire and the OSPF process is done initializing in the router, a hello will go out the door. I don't think there's any like wait process.
Mm-hmm.
There is a wait process for certain things like database exchange, for example. Once they've already found each other, the hello process has happened, then there's a wait process to determine who is going to send the database first. But for hellos, I don't think there is. They're going to exchange hellos, but I'm not positive without actually looking on the wire to see if there's like. Yeah, I don't think so. I don't think there's any. I know the question you're asking, but I don't think there's any. Do I wait for a while before I send a hello out or anything like that? No. Okay. And now there is another, like if there were more than two routers on the wire, like say it's an Ethernet segment of VLAN and you got, I don't know, 5 OSPF routers sending hellos, there is going to be a designated router process that we go through.
And that does have that I know router. Has a wait time.
There is, yeah. And there's a process to that to actually elect the designated router and the backup designated router. But we're not there yet.
Yeah.
Let's just get through like the two router scenario where they've discovered each other. We've exchanged hellos. They now know about each other. And they're going to go through some phases here. So there's a whole bunch of, state, I should say. So there's a state to forming the relationship between the OSPF routers. There's the initial, like let's say it's R1, router 1, and we got R1 and R2, router 1, router 2. Router 1 sends its hello. Hey, I haven't seen anybody yet, but this is me. And then router 2 sees that hello. Hell yeah, I just saw your hello, and this is me. And by this is me, that's the router ID that is going to be encoded in the hello message. So I haven't seen anybody yet, this is me. We have no state yet because the routers haven't talked to each other. Router 2 responds with its own hello message, with its own router ID and the router ID of the hello it saw. That means we're now in init state between R1 and R2, initialization state. R1 responds again. I saw your hello. I know you saw mine. Now we're in a two-way state. They've both seen each other and acknowledged via router IDs embedded in the hello message that they've seen each other. So we've moved from the initialization state to now the two-way state. That is, the routers know about each other. They've acknowledged to each other that they know about each other. And now we're at an important point. Once we've reached the two-way state, we're ready to do something super important to OSPF. And that would be what, Holly? What is the important thing we're ready to do next?
Well, the key thing in OSPF, as we mentioned earlier, is that you need to start sharing your link state database information. Because without that, you can't run the shortest path first protocol. So you just know about each other and you're not actually doing OSPF yet.
Right.
So
Exactly right. So we've gone through the very initial discovery part. Now we're like, okay, now that we know about each other, let's exchange our link state database information. Well, okay. So now is an interesting question. How much of the link state database do we exchange? And this is interesting to me as I reviewed this. As I haven't preparing for this show, I hadn't thought about this process in quite some time. And if you'd asked me before I reviewed this, I'm like, I would have just dumped the whole database. Here's everything. Blah. However many thousands or millions of link state database records I might have had, you can have it all. But that's not what happens actually. You don't exchange by default just because it's a new neighbor relationship, your entire link state database. Instead, we exchanged lists with each other of what's in our link state database. Here's a list of all the stuff I got. I'm not going to give you all the stuff, but here's a list of all the stuff, and you can pick off the list what you want, and then I'll send that to you. So that's our database description. Go ahead, yeah?
Yeah, I was going to say, I'm assuming now because we've got to have our databases matching. I might have some things and you might have some things. Yeah. So I only need to take what I don't have and you only need to take what you don't have so that once we've exchanged all this info, we've got matching databases, right?
Yep, that's exactly it. Here's what I got. I have all of those. I don't have those 10 things though. Oh, okay. Send me those 10 things. I have everything but those 6 things. Okay. Yep. I'll send you those 6 things. And there is a process here as to who goes first, who's going to exchange link state database information with who first. So there is so we're going to move from the two-way state to the X start state, the exchange start state, and the routers negotiate. You were just going through this in your studies, the master-slave relationship to determine who's going to send the first database description packet. Database description being not what's in the database, but the list of things that you could get from the database if you want them.
And to relate that back to those packet types, because that's kind of, when I was going through my studies, shall we say, that's kind of where I was like, okay, well, this is really helpful, but that data description packet is now a type 2 packet. So they kind of chronologically follow the states and those packet types, and they all fit together, which I think sometimes the link between those two isn't there, or maybe it's just not as obvious. But I think it's important to understand that in this state, we're now exchanging this type of packet. And I think that really helped me with troubleshooting as well, to understand, okay, well, what am I expecting to see here?
So we go through the exchange start state, and we have that determination of which side is going to send their database description packet first. And now we go to the exchange state. Each router looks at the other one's list and asks for whatever link state advertisements it's missing. That's our link state request packet. That's going to happen there. So we go to the exchange state. Okay, I see from the list that I'm missing these things. Please send me these LSAs. I'm going to send you a link state request for these LSAs that you have. And now we move, that's the exchange state. Now we're going to move to the loading state. Each router is going to send the other one whatever LSAs were requested in their link state request packets. And the loading state is done via LSUs, link state update packets. And the link state update packets contain the link state advertisements that each side wanted to know about. Once that's complete, we're finally at the state we've been waiting for, the full state. We're fully adjacent neighbors. We're not just two-way neighbors. We're fully adjacent neighbors. We're now full, completed our link state databases. Our link state databases should now look exactly the same. They've been synchronized between the two routers. And going back, I think we covered this in the last episode. Why do we have to have identical link state databases between OSPF routers that are in a common OSPF network?
Well, now we've got our full neighbor state. We've got to start calculating what this optimal route is. And what's important here, and I actually only learned this week, or maybe only realized it, is that each router is actually going to perform the algorithm. So if we have different databases and we are all running an algorithm, we're going to get different outcomes. We're going to get different shortest paths. Now, how on earth do we know what the shortest path is if we've got different databases and different routes, and now there's just a lot of complication, a lot of mess. So it's really important that we all working off of the same database so that we all know what that same shortest path is going to be from me to you or whatever, vice versa.
Yep. Now, one subtle thing here, every router is calculating the shortest path first algorithm. They're doing that Dijkstra calculation that you, I think you explained it from your because it's not unique to OSPF. The Dijkstra algorithm is used in lots of different applications that you studied, even though you weren't a computer science major. It came up in your work. But every router is going to run that calculation from its own point of view.
Mm-hmm.
And so it's going to be shortest path, router 1's point of view, and from router 2's point of view, and from router 3's point of view, et cetera. But yes, they have to have the same identical link state database so that they are performing their shortest path first calculations correctly and come up with the same, what should be, again, from its own perspective, but the same shortest path through the tree.
I do have a question just on the states, which maybe you'll be able to answer. So
maybe.
In my experience, when it comes to troubleshooting going through these states, most of the time I find that like it gets stuck in usually, the init state or the two-way state, but I find I'm yet to have a situation where it gets stuck after it starts exchanging, or like that X start has been, we're in that state. Usually it's pretty smooth after that.
And fast, yeah.
Yeah. Have you ever seen it get stuck in like those later stages? Just out of curiosity, really.
Not that I've experienced, no. I actually want to devote an episode to reasons we can get stuck in different states, because there's a bunch of troubleshooting that we can do. Because there's a lot of reasons why neighbors won't form, or why neighbors are doing weird things, because you can have timers that are out of sync. You can have problems like the MTU size is mismatched between interfaces on either side, can cause an OSPF neighbor relationship to fail. You can have areas can be mismatched, that'll cause it to fail. And a variety of other things. Mm-hmm. So that was something I did want to kind of walk through, what you'd see and what that might indicate is the problem based on what state you're seeing. I haven't in real life ever run into a problem like I'm stuck in the X start state, or I'm stuck in the exchange or the loading state. Nah, I've never seen that. I've seen neighbor flaps where it's like one side had a timer that was different than the other. And so it was like, oh, my dead timer has gone off because the hello timer was mismatched on the other side. And so the dead timer on the far side was like, I think you're dead, because I haven't heard a hello from you in a while, because it wasn't configured right by the engineer. Stated well. Okay. Well,
leads us into what is a dead timer?
What is a dead timer? So let's talk about hello packet intervals and dead timers. So this we're getting the answer ahead of the question, but the question is, how do OSPF neighbors keep track of each other? That's really the question. How do two neighbors that have established a relationship know that the other one's still there listening, still alive? Because if it goes away, that implies, oh, that router's gone, and what my link state database looks like is probably different now. We need to do something about that. So how do they keep track of each other? And the default way they keep track of each other is with hello packets. Mm-hmm. If you keep sending a hello to your neighbor, yeah, I'm still here. Yeah, I'm still here too. And the hello packets are just going back and forth between the two of them on a regular interval.
Do we know what that interval is specifically?
I don't know if the defaults are the same across all vendors, but I know in Cisco land, the default is 10 seconds. And I would hope all vendors are the same, because if you had like a Cisco box and a Juniper box and you just wanted to make them OSPF neighbors, something you should totally be able to do. OSPF is a standard. But their hello timers were different defaults. That would blow things up potentially. But do you happen to know what the Juniper defaults are?
No, I don't actually. That's myself. No, didn't come up either. No one. In my training, I guess I assume it must be the same, because I'm assuming that that's a protocol standard would be the interval, not.
That was another thing I actually meant to look up and didn't. Is there an RFC defined, like what the default standard is? But another thing here though is, for modern networking, if the hello packet interval is 10 seconds and we wait for 4 times the hello interval. That is, I've missed 4 hellos from you before I decide you're not there anymore. That's a long time. That's
Yeah.
40 seconds for your dead timer to expire, and then the OSPF process to decide that the neighbor is not there anymore. 40 seconds. So it's not uncommon for engineers to tune these timers to be more aggressive so that you detect your neighbors down more quickly, and then can react and go through convergence. We talked about convergence in an earlier episode, just the act of something's changed in the routing domain and we need to go through our recalculations of whatever they are, run our SPF again in the case of OSPF, or run in the case of Cisco's EIGRP, the dual algorithm, and see what shortest path is through the network once again.
So hello packet intervals, RFC 2328.
Oh, look at you Googling. Okay, so does it give us like
it's 10 seconds. That's the...
It is 10, okay.
Yes.
So then presumably all vendors would conform to that, although, again, that is a really long time in network land to wait for a detection of your neighbor going down. And now there are lots of ways you can deal with this. So you're nodding your head and you're about to say something. Did you have some ideas on this?
No, more so just it's a long time depending on how your network is set up. Because if you've got alternative paths and redundancy, which you should, then, you should have alternate routes. That maybe if that is down within 40 seconds, it's going to be less optimal routing, but hopefully you won't lose too many packets.
Okay, so here's an important point. So if a router goes down, and we go through the default of the 4 times the hello interval before we decide it's dead, that's 40 seconds that you think there's a router you can send traffic to that isn't there. He's gone.
Yeah,
so you're sending traffic down the line to a router that's not there anymore. That traffic's dead. It's going nowhere. There's no one to receive it on the other end. You're sending it as if it is there, but it isn't. So there's a black hole for 40 seconds where that traffic goes nowhere.
And it's not TCP, so you're not getting any acknowledgements regardless. So it's not like you're sending it and you're seeing nothing's coming back.
Okay. I mean, the traffic, but remember what it is that we're sending to the router. It's any traffic that it's not just OSPF traffic, right? It is any traffic that we are routing through the network that we are expecting that router to be along the shortest path for whatever that destination is. So it's user traffic, it's HTTP traffic, it's whatever that traffic is that's supposed to be routing through. Let's say it's R1 routing to R2. R2's dead, but we don't know it yet because the dead timer hasn't expired. We're forwarding traffic from R1 to R2 because R2 is the shortest path for whatever the destination is for this traffic. R2's not getting it because it's dead. It's not listening. It crashed. Line went down, whatever the problem is. But for that, until that dead timer expires, we're sending traffic to nowhere. It dies. Now, that traffic is probably TCP or UDP or whatever, and so it will be retransmitted.
But I guess you can't rerun, like you can't pick the shortest path until you've shared your updated database. And you're not going to do that until you receive the dead time and know this guy's no longer on the network.
You got it. So
After
we're
40
not
seconds.
going to reconverge until that dead timer expires. That's the problem. That's the problem right there. And so in modern networking, we definitely want a faster convergence time than the default behavior of 4 times the hello interval. And so then this is the point I wanted to raise, that there are mechanisms to help deal with this. One is, tweak your hello timers. Make the hello timers be something smaller than 10 seconds, and figure out what's reasonable for your own network. Another tool is BFD, bidirectional forwarding detection, which is It's not a routing protocol, but it is a tool to detect that the path between two routers has failed, and to do so very quickly in milliseconds or even microseconds. And then BFD will, it'll basically just say, hey, guys, skip the dead timer thing. This link is dead. This router is talking to, he's gone now. Just assume he's down. Please converge. And BFD, bidirectional forwarding detection, is an extra tool that can communicate with a variety of different routing protocols, including OSPF, BGP, and so on. You're nodding your head like you've heard of BFD. Is this come up for you?
Yeah, and I've implemented it for this exact use case of a customer who isn't happy with reconvergence time. They're looking for something to speed up that process, and a fellow SE of mine recommended BFD, and that's exactly the use case.
Yeah. And there's another scenario here that I think is interesting. Imagine you've got R1 and R2, and if they are directly connected via a physical wire, you've got an Ethernet cable that are linking the two of them together. If that link goes down because R2 crashes, let's say, and the link goes down, R1 will know in that case right away, hey, that link is down. It's not going to wait for the hello timers. It should know at that moment, oh, bang, that link is down. I've got to reconverge. What if R1 and R2 are connected through a switch, though? R2 goes down. Does R1 know? Well, R1's link to the switch is still up. In that case, it would have to rely fully on the hello timer and then the dead timers to expire, because he'd still have line signal from the Ethernet switch. Wouldn't know that R2 was gone. So I wanted to point that out as another difference, another scenario to consider. A lot of people would rather interconnect the routers through the switch or through a switch network for some reason, or maybe need to just because of what their physical layout is. But you end up with that problem where I've still got line on R1 because I'm talking to the switch, have no idea R2 is down, as opposed to that physical link between R1 and R2 directly. The link goes down. Aha, I know right now I don't have to wait for hello timers to expire anymore. I know that link is down, and I'm going to reconverge and begin routing traffic through a path that still exists. My alternate path that you were talking about before, because there should be, hopefully, there's a different way to route that traffic that we can converge on. All right, what questions have you got with all that?
No questions. I guess I never got to the point where I thought about what happens if there's a switch in between, and it's a very good point.
Yeah, and again, the magic of BFD solves that bidirectional forwarding detection, which we can devote a whole episode to bidirectional forwarding detection. That's a whole thing unto itself. That would be interesting.
Again, we devote an episode to it, but is there any reason why you wouldn't want it? Because I think if you're listening to this, you're like, oh, well, it sounds like a no-brainer to have BFD if, instead of waiting 40 seconds.
Back in the day, there was some question about whether the hardware supports BFD, because BFD is a pretty intense process, and so you needed hardware that could actually support BFD, so it's not a burden on the device. And whether that's much of an issue in 2025 or not, I'm not sure. Certainly, any significant kind of router or switch is going to be able to handle that. It's going to be baked into the hardware ASIC. It's just going to be able to deal with it. But there's a lot of, considering that BFD can react in milliseconds or even microseconds, imagine running that in software, constantly sending out traffic and then waiting for it to get a response back or not. That would be a computationally intense thing. So as far as I know, BFD relies heavily on the ASIC supporting it, and that would be the big question.
Okay.
Aside from, it's like if it's there, configure it and turn it on, make it go. But I have tended to think of it as something that isn't turned on by default. A lot of engineers just, won't, unless they're just really concerned about that, that rapid convergence time, because they have stable networks and they've never run into the problem. And so why would I add BFD to the mix? It complicates my life. That sort
Fair.
of logic.
Yeah.
All right, one more thing we really got to talk about before we're done this one, and that is going back to our comments about designated routers and backup designated routers. Do you remember the scenario where these come into play?
As in when we turning on the network, or as in reconvergence, or...
Let me ask the question a different way. Do we always, on every OSPF network segment, have a designated router and backup designated router?
Yes. But there's always a designated router, no?
It depends on the network type. It depends on what OSPF network type, and we haven't talked about OSPF network types. Again, there's a whole other episode here to talk about OSPF network types, I think. But there are broadcast OSPF networks like Ethernet. There's point-to-point network types. There are non-broadcast multi-access and other ones. I didn't even dig into that whole list. And depending on the network type, you end up with the designated router, backup designated router election process going on. But you don't need one on a point-to-point network type, because on a point-to-point network, you just got two routers on either end of the link. That's it. So those two are gonna talk to each other. In the scenario of an Ethernet VLAN, let's say, with a bunch of OSPF routers, let's say there's 5 of them that are plugged into the same VLAN and they can all see each other. The point of a designated router is to be the point man, if you will, to share link state database, LSA exchange, to exchange all of the information with everybody else. If you've studied BGP and you've run into route reflectors, kind of like that, kind of like a route reflector in BGP, which if you haven't studied BGP and you don't know what a route reflector is, never mind, I didn't say that, but it's a similar kind of idea where there's one router that's the one that's going to tell everybody else what all of the different, in the case of OSPF here, link state advertisements, the link state information is going to be exchanged through the designated router. And so what you don't end up with then is 5 routers and an Ethernet segment, and everybody is fully exchanging their link state database with everybody else in this full mesh where it's like bang, 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 all of this information. Everything instead goes through, I'm going to tell you, designated router, and you, designated router, tell everybody else about my LSAs. That reduces the amount of communication that's going on and calms down the amount of CPU utilization that would be taken up, because you're only talking to one router and you're relying on that one router to talk to everybody else.
So other than point to point, are there any other times where you don't have a designated router?
I have to look at my list and see.
Who has a point-to-point network running OSPF? If you have 2 routers, why are you doing OSPF?
Because of the type of link. So like in a WAN link, you might have the remote office is on one end of that point-to-point link and your head office is the other end of the point-to-point link. It's not a mesh.
Yeah.
So there's times, and you will set up your individual OSPF links with what the network type is that you want to use. In fact, if you could be on an Ethernet segment, which will default to an OSPF network type of broadcast and say, nah, this is actually point-to-point, the way it behaves. So even though technically, it's Ethernet and it's on a broadcast segment, I'm going to tell it as the network engineer, hey, you're a point-to-point link. Behave that way. And that you do away with the whole designated router, backup designated router thing. Because you don't need it. Why would you add that overhead to the OSPF process? You can just say, behave like a point-to-point link, because functionally, topologically, you are a point-to-point link. Make sense?
Yeah, it's interesting. I've never come across OSPF types, actually.
Oh, okay. Well, then maybe that's probably the
Well,
next episode.
I'll
Then we
let you
should talk
know
through
in the
that.
next modules that I cover if it comes out, if it comes up there. But it's
Well, part of it's history, honestly. Like there were like you doing frame relay networks way back in the day. That, if I remember right, those were by default non-broadcast multi-access, and you had to set
mhm.
up OSPF across those links in a particular way, just because frame relay was weird compared to a lot of other network types. I'm going from memory here, so if you're going, no, Banks, frame relay wasn't non-broadcast multi-access, you're probably right. I'm sure. I didn't look this up before this. So send your well actuallys to packetpushers.net/follow-up and remind me of what I'm forgetting. But between now and I
Yeah.
think next episode, Holly, we can review the different OSPF network types and do a show on that because it does. Just because so much today is Ethernet, that's the handoff you
Yeah.
get. You don't really have to think about it so much. Historically, depending on the kind of network you were plugged into and what your service provider was handing you and what sort of a circuit it was, your OSPF network type probably mattered a lot more. And what that behavior was with your OSPF routers connected to that link type mattered to you. Now, point to point or broadcast, those are the kinds you care about. You maybe don't care beyond that too much. You don't have much use case for any of the other ones, but we'll talk about them. We'll talk about
Yeah.
them. For our purposes today, I just wanted to highlight that with an Ethernet segment, which is most likely what your OSPF router is hanging off of. You've got a broadcast segment, and if you've got a bunch of OSPF routers plugged into that broadcast segment, there is going to be an election of a designated router and then a backup designated router. And the point is, we don't want a full mesh of OSPF routers doing these link state database exchanges with each other. Let's route everything through the designated router. Also, a bit of history in that back in the day, if you had this, you'd take your most powerful router and make sure that that router was going to be the designated router because he had the most CPU to deal with this. And your less powerful routers could be relieved of some of the CPU burden of handling the link state database exchanges between itself and everybody else that was on the segment.
Mhm.
Nowadays, there's enough CPU out there on just even a low-end router that does the designated router role matter as so much? I mean, probably not so much. And so you wouldn't be as concerned about making sure that a particular router becomes the designated router. You just kind of, it maybe doesn't matter that much to you. Historically, again, you probably did care a lot. You'd want your big router with all the extra CPU to become your designated router, and so you'd manhandle the election process by setting the priority, the OSPF priority, or setting the loopback address to
Mhm.
something very particular, so that the designated router election would be won by the router that you mean to be the designated router. Now, one final point here on this is we were talking about full and two-way states. If I'm the designated router and I do my, in Cisco land, it would be show IP OSPF neighbor, what would my states be with all of the other routers on the segment? Would it be full? Would it be something else?
Should be full.
It would be
Yeah,
full, yeah.
if everything is
Because
correct.
because the
Yeah.
designated router is the guy that's actually doing the exchange of LSAs.
Mm.
And so if I'm exchanging data, I'm fully adjacent. I'm a fully adjacent neighbor. Now, if I go to a non-designated router
Yeah.
and do show IP OSPF neighbor or whatever it would be in Juniper land, I'm not sure. And I get my listing of OSPF routers, what would my different states be? I'd have full, we've already said, to the designated router. What would my state be to the non-designated routers?
Well, if I try and think if I think about it in this a logical way, right? you know it's a neighbor, but you're not necessarily transmitting LSAs between those because it's going through the designated router. So I would think we'd be in a two-way state where we know it's a neighbor, but we're not exchanging LSAs.
Yep, exactly. You'd be two-way. We know about each other, but we're not doing database exchange because we're on a broadcast segment. You're not the designated router, so hi, it's nice to know about you, but we're not exchanging information. So exactly, two-way. Because they're not exchanging link state database data. Yeah, exactly. Now, there's more we could talk about, getting into like how exactly the designated router is elected, what happens, how the backup designated router is elected, and then what happens when the designated router fails, and and so on. There's a lot of things there that you might actually care about if you're a CCNA or a JNCIA candidate. But we're coming up on an hour, Holly. We should shut up and stop talking now. Boy, another half-hour program we crammed into an hour. So
yeah, this was expected. I looked at this and I was like, yeah, we're gonna be chatting for a while.
I expect them to go this way too. It's just the way of it. It's just the way of it. All right. Any final questions or comments about what we covered in OSPF today before we close it down?
I think there's so many more questions that lead off of this episode, so we'll have to do another one. But I think this was a great, or three, but I think this really set the stage and helped actually clarify some of the things that, I looked at in my training and then didn't really get into the nitty gritty or didn't fit it into the right place. Like, that protocol 89 thing. And I love actually doing this side by side with things I'm learning in my day to day, and we can come and chat about it, and hopefully I can bring some questions that other people might have come across as well.
Awesome. Well, all right, let's call it for today then. And if you're out there still listening, thank you for listening or watching. And as for networking, you can send your comments, your love, and your well-actuallys to packetpushers.net/follow-up, or you can join the community Slack group at packetpushers.net/community and tell us in the N is for Networking pod channel. We get lots of feedback from all of you, and we love it. It is awesome to get so many comments from you saying how you enjoy the show, or errata, things that we got wrong that you need to tweak. And we're going to be addressing these in future episodes, we promise. Someone had the idea of, like, you guys should have an errata page where you list all the little details of things that need to be tweaked. Yeah, it's a good idea. It's a good thought. We might actually do that. So like, subscribe, tell your friends. We'd appreciate that. And as for networking is climbing the ranks of the many Packet Pushers podcast series, and Holly and I want this show to be #1 eventually. So if you would help us out by letting the world know about this show, we'd appreciate that. We are everywhere that you get your podcasts, including YouTube, where you can see Holly and me chatting with each other if you'd like that version of this show. Until then, just remember, networking isn't hard. Other people figured it out, so you can too.